Welcome back to Behind the Pages. Last episode, we built a planet. We discovered how Noet's atmosphere regulates temperature, how storms become its clock, how infrared radiation warms the world, and how a red dwarf star can support a habitable planet. But building a habitable planet isn't the same as creating life. One question still remained. How does life actually begin beneath a red dwarf star? Ironically, the answer introduced one of the greatest paradoxes I found while researching Noet. Life needs ultraviolet light, but too much ultraviolet light destroys it. One thing that fascinated me while researching this was how closely the scientific questions echoed the opening of Genesis. The Bible begins with darkness, chaos, water. Then God says, "Let there be light." Light marks the beginning of order. Today, origin of life researchers ask remarkably similar questions. Not, is light important, but what kind of light is important? Because different wavelengths do different things. Earlier, we talked about infrared. Infrared warms planets. Ultraviolet does something completely different. Ultraviolet carries much more energy. That energy can drive chemical reactions. Many scientists believe UV light helped kickstart the chemistry that eventually produced the first self-replicating molecules. In other words, too little UV light, life may never begin. Too much UV life never survives. Immediately, I realized that was another problem Noet had to solve. Last episode, as we built Noet's atmosphere, another question was raised. How does that atmosphere survive for billions of years around one of the most violent stars in the galaxy? Red dwarfs aren't simply smaller versions of our sun. Their magnetic fields are far more chaotic. Because many red dwarfs are fully convective, their interiors churn from core to surface, generating tangled magnetic fields capable of producing enormous stellar flares. Some of these super flares release hundreds or even thousands of times more energy than the largest solar flares of our own sun has produced. For a planet orbiting so close to its star, that's a problem. Not because every flare strips the atmosphere away, but because every flare takes a little piece of it. Over millions and billions of years, that gradual erosion becomes significant. So the question isn't, can the atmosphere survive one flare? It's, can it keep repairing itself faster than it's being worn away? Instead of imagining a static atmosphere, I started imagining a living one. Fortunately, the atmosphere doesn't stand alone. The planet has several layers of defense. First, a powerful magnetic field generated by massive molten iron core deflects much of the incoming charged plasma. Most of the time, that shield bends and redirects the stellar wind before it can reach the atmosphere below. During the largest superflares, however, even the magnetic shield can become compressed or briefly torn open. The atmosphere is exposed. Auras ignite across much of the sky. Small amounts of atmospheric gas escape into space. But the system doesn't collapse because Noet is constantly rebuilding itself. Volcanoes continually release water vapor, carbon dioxide, nitrogen, sulfur compounds, replacing gases that have gradually been lost. Meanwhile, the defense cloud decks protect the lower atmosphere where most of the planet's water is safely stored beneath the turbulent upper layers. The atmosphere isn't immortal, it's resilient. One question still bothered me. If red dwarf stars continually batter nearby planets with powerful stellar flares, how does Noet keep its atmosphere for billions of years? To answer that, I first had to understand what the planet was actually fighting. I discovered there are two different threats. The first is the stellar wind. Think of it as a constant breeze flowing outward from the star. Our own sun produces a solar wind, a continuous stream of charged particles that washes over the entire solar system every second of every day. A red dwarf star has one too. It's simply called a stellar wind. On its own, that steady flow slowly chips away at the upper atmosphere over incredibly long periods of time. But then there are also the stellar flares. A flare isn't the wind, it's an explosion. When tangled magnetic fields inside the star suddenly snap and reconnect, they release enormous bursts of energy. Those flares flood nearby planets with intense ultraviolet light, X-rays, and high-energy particles. Sometimes they're also accompanied by a coronal mass ejection, or CME, a gigantic cloud of magnetized plasma hurled into space at millions of miles per hour. If the stellar wind is like standing in a strong breeze, a stellar flare is like being hit by a hurricane. The wind slowly wears a planet down. The flares deliver powerful blows that can temporarily overwhelm its defenses. That made me wonder, how does Noet survive both? At first, I assumed the answer was simply a stronger magnetic field, but that only pushed the problem one step deeper. Where does a magnetic field come from? It turns out, planets don't simply have magnetic fields, they have to generate them. Deep beneath Earth's crust lies a massive iron-nickel core. The outer portion of that core isn't solid, it's liquid. As that molten metal continually circulates with Earth's rotation, it behaves like a giant electrical generator. Scientists call this the geodynamo. That geodynamo produces Earth's magnetosphere, an invisible magnetic shield that deflects much of the stellar wind and helps protect the atmosphere from being gradually eroded. During especially powerful flares, the magnetosphere can be compressed or partially breached, but without it, the atmosphere would be far more vulnerable. Mars provides a fascinating comparison. Evidence suggests Mars once had a global magnetic field, but because Mars is much smaller than Earth, its interior cooled more quickly. As its core solidified, the geodynamo shut down. Without a strong magnetic shield, the solar wind slowly stripped away much of its atmosphere, leaving behind the cold, dry world we see today. That immediately raised another question. If planetary interiors naturally cool over time, what keeps Noet's heart beating for billions of years? The answer wasn't the star. It wasn't the atmosphere. It wasn't even Noet itself. It was the rest of the planetary system. Noet is tidally locked. One side always faces the red dwarf. That never changes. But tidal locking doesn't mean the planet is motionless. Far from it. One of the most important discoveries I made was realizing that Noet couldn't exist by itself. It needed neighbors. In particular, it needed a massive sister gas giant farther out in the planetary system. Not because the gas giant protects Noet directly, its magnetic field doesn't stretch across space. Instead, its immense gravity acts like a cosmic stirring spoon. As the gas giant travels along its own orbit, it continually tugs on Noet and other neighboring planets. Those gravitational interactions prevent Noet's orbit from becoming a perfect circle. Instead, the planet maintains a very slight oval or eccentric orbit. That tiny imperfection changes everything. Although Noet always keeps the same face pointed towards its star, its shape is constantly changing, ever so slightly as the competing gravitational forces pull and release it. The entire planet is continually being stretched, relaxed, then stretched again. Astronomers call this tidal heating. It's what will keep the inner core still melting and boiling. It's the same process that makes Io the most volcanically active body in our solar system. Gravity becomes friction. Friction becomes heat. Heat keeps the mantle soft. The soft mantle keeps the iron core molten. The molten core generates the magnetic field. The magnetic field protects the atmosphere. The atmosphere protects life. Suddenly, I realized Noet wasn't surviving because of one lucky coincidence. It was surviving because an entire planetary system was quietly working together. That magnetic shield deflects much of the charged plasma carried by the red dwarf stellar wind. Not perfectly. Some of the atmosphere is always lost. The continual tidal heating keeps Noet's iron core vigorously churning. That gives the planet a magnetic field even stronger than Earth's. Most of the time, it easily deflects the steady stellar wind. Even during powerful stellar flares, the magnetosphere absorbs much of the impact, compressing like a spring before expanding back into place. The atmosphere isn't left defenseless. It simply endures another blow. At first, I thought that constant loss sounded like a flaw in the system. Then I realized it might actually be part of the balance. Deep inside Noet, tidal heating continually fuels volcanoes. Those volcanoes release enormous amounts of water vapor, carbon dioxide, sulfur compounds, and other gases into the atmosphere. Left completely unchecked, those greenhouse gases could gradually thicken the atmosphere until the planet becomes dangerously hot. Meanwhile, the stellar wind is continually carrying a small amount of the upper atmosphere away into space. The same tidal heating that keeps Noet's heart beating also has another consequence. The planet never truly rests. On Earth, earthquakes are usually caused by tectonic plates slowly slipping past one another as internal heat escapes from the planet's interior. Noet is different. Its crust is constantly being flexed by gravity itself. As the red dwarf and neighboring planets tug on Noet's slightly elliptical orbit, the entire planet stretches, relaxes, then stretches again. The surface doesn't simply crack once in a while. It continually does so under stress. That means the people of Noet don't just experience earthquakes, they experience what I come to think of as Noetquakes. Not isolated disasters, but a near constant rumble beneath their feet. In many places, the ground is never completely still. The crust breathes with the planet. Instead of building up stress for centuries before releasing it in one catastrophic event, much of that energy escapes continuously. The crust is thinner, more fractured, more flexible, and wherever those fractures open, magma rises. At first, that sounded like a nightmare. Then I realized the volcanoes are doing exactly what the planet needs. Every eruption releases water vapor, carbon dioxide, nitrogen, sulfur compounds, all of the ingredients needed to replenish the atmosphere. Those same gases help build the defense cloud decks. The cloud decks shield the surface from the most dangerous ultraviolet radiation. The atmosphere redistributes heat between the eternal day and eternal night. The magnetic field protects that atmosphere from the steady stellar wind, and the volcanoes continually replace the small amount that is gradually lost. The solution wasn't eliminating ultraviolet light. The solution is regulating it. Early in a planet's history, cloud cover may be patchy. Volcanic eruptions continually inject water vapor into the atmosphere. Openings in the cloud allow enough UV light to reach shallow oceans where prebiotic chemistry can begin. Later, as the atmosphere thickens, the cloud decks become nearly permanent. Now, those same clouds protect life from the violent stellar flares. The planet changes as life changes. I started thinking of Noet as a living organism. Its molten core is the heart, its volcanoes are the lungs, its atmosphere is the breath, Its cloud decks become the skin, shielding life from the harshest radiation. Its magnetic field becomes an invisible immune system, protecting everything beneath it. Every super flare leaves a scar. Every volcanic eruption begins the healing. That became one of the central ideas behind Noet. Not perfection, transformation. Not because the planet never experiences suffering, but because it continually responds to it. Life doesn't survive because nothing ever goes wrong. Life survives because the whole planet is continually renewed. As I sat back and looked at the whole picture, I noticed something I hadn't planned. The same pattern kept appearing at every scale. Individual cells heal. Human bodies heal. Communities recover. Forests regenerate after fire. Planets recycle their atmospheres. Entire ecosystems depend on countless interconnected systems working together. Whether someone describes that pattern as creation, emergence, or simply the remarkable order of nature, I found myself seeing the same design echoed again and again. It reminded me of something often described in mathematics and art as fractal patterns, where similar structures appear across different scales. Not because everything is literally identical, but because the same kinds of relationships repeat. I couldn't help wondering whether that was part of God's fingerprint on creation. That when you build a world using the materials God has already woven into creation, those echoes begin to appear naturally. The more I researched Noet, the less it felt like I was inventing a planet. It felt like I was discovering how many things have to work together before life can exist at all. Earth is often called a rare planet for exactly that reason. Its habitability depends on an extraordinary combination of factors: a stable star, liquid water, a magnetic field, plate tectonics, an atmosphere, the right chemistry, the right distance from the sun, and countless other interactions that all have to remain in balance. Building Noet gave me a new appreciation for our own world. The further I dug into astronomy, geology, chemistry, and biology, the more I realized that life isn't sustained by one miracle. It's sustained by thousands of interconnected ones. I think that's why Noet ultimately became a story about the main character, Sarah, because her journey isn't about becoming perfect, it's about transformation. Just as Noet survives through continual renewal, Sarah must learn the healing isn't a single moment. It's a lifelong process of allowing what is broken to be restored. By this point, Noet had become far more than a single planet. It had become an entire planetary system working together. The neighboring worlds aren't simply distant objects decorating the sky. They are helping keep Noet alive. They stirred its molten heart. They fueled its volcanoes. They helped sustain its atmosphere. And they shaped the rhythm of life itself. But there was one discovery I hadn't expected. When I removed Noet's moon, I thought I had created a problem. Instead, I found something even more fascinating. The neighboring planets became the moon, not just visually, but culturally. That they became the calendar, they became the tides, they became the clock. Their immense gravity reshaped the oceans, the coastline, and perhaps even the earliest steps toward life itself. And because these planets orbit so closely together, they wouldn't appear as tiny points of light. They would hang overhead as enormous neighboring worlds, each one changing phases, passing in front of one another and marking the passage of time across the sky. In the next episode, we'll explore those crowded skies. We'll look at the giant sister planets that dominate Noet's heavens, how they replace the role our moon plays on Earth, and how the entire civilization learns to tell time by watching planets instead of moons. I'll see you then, and in the meantime, continue creating, because every world begins with imagination.